So I'm Ryan Hallisey. I work at NVIDIA. This is my colleague Alay Patel, and like I said, we're going to be talking about the Kubernetes control plane. So the story to think about here is GPUs are being released every 1 to 2 years. They're getting more and more powerful, and so more powerful means theoretically we can support more workloads. More workloads means we can have more secrets, more volumes, more objects. And all this is pressure on the API server. Right, so we can do all these things, and what we want to do is we want to make sure our control plane, our Kubernetes control plane, is still running. So we did an experiment where we wanted to, as a bare metal provider, somebody who runs on bare metal Kubernetes, we wanted to see if we could scale the compute independently of the control plane. So this experiment, what we had in mind is we would take our control plane and we'd say, okay, let's have a fixed set of memory and CPU, and let's scale up our compute, and let's see what happens. So we keep control plane resources constant, and we want to see how it performs. So it went perfect, right? Not exactly. I like this title, Incidents, Incidents, Incidents. So there's a few things that went wrong. We're going to talk about 3 of them. I'm going to talk about the first one. The first one, first big thing we encountered, a large number of list calls to secrets would lead to control plane outages. And these aren't ordinary secrets, let me tell you. Can I go to the next slide here? There we go. Okay. We noticed that in our environment, if we have a lot of secrets, we can run into an specifically if we do list calls to the API server. And so these secrets, like I said, they're not quite the ordinary secret. They're not like a base64 encoded string that's like a few hundred bytes. They're 0.2 megabytes each. They're pretty large. And we have 5,000 of these things. So think about that in terms of etcd storage. So we have etcd storing these things. So that's okay. But now when you do a list call, think about all that information that needs to go into the API server, into the cache, and think about how much memory that consumes. And so if we do 2 concurrent list calls, we can get a ton of this stuff built up in the cache, and we can run out of memory in the API server. So this is a big problem for us, and you can kind of see it in the picture on the right. When we do these list calls, it was pretty obvious that we would just, it would and we'd lose all our metrics for the API server. Okay, so what was our solution? How did we deal with this? Well, we used API priority and fairness to help us. API priority and fairness, if you don't know much about it at a high level, it's this idea that you can have specific REST calls made to the API server. They can be given certain levels of priority. So think of like the API server as a shared resource. We want to make sure that your patch requests, your put requests, your list requests can all get there, and they'll have a fair shot of reaching the API server to process those things. So you can use API priority fairness to say, well, we only want to allow 2 concurrent list calls to be executed. And this was really helpful for us. It actually is what solved our problem and what kept us within the safe area of memory. We won't want to go over 2. So we would make that a part of our API priority and fairness policy. And this is what would save us, right? With this, all these many secrets and how they're constructed, we needed to use API priority and fairness to protect ourselves. So this is great. This significantly reduced our and was able to get through the problem. And if you want to learn more about API priority and fairness, there's actually a talk. Unfortunately, it's given at the same time as this one, but the QR code's there if you want to watch the recording afterwards. It'll go through in detail and much more detail about how API priority and fairness works. But this worked great for us. It protected our API server. So that was problem number 1. Alay is going to take us through the next 2.
Thanks, Ryan. In the next few set of slides, I'm going to continue talking about the problems that we hit at scale and some of the fine-tuning techniques that helped us to solve those problems. So you can see the graph here, which is API server memory utilization. You can see between 6 and 800 hours, there is a gap. That gap is an API server restart. The more interesting thing about that is after the restart, API servers came back with 30–40% less memory utilization. We actually saw this consistently happen in our fleet, that anytime we would rolling restart API server, it would come up with less memory utilization. Even if the workload on that cluster was same, it would end up come up with less memory utilization. So we started wondering, is there a chance to optimize some of the way garbage collection happen? Is the memory not being garbage collected fast enough? So that's where we started looking at GoGC. GoGC is a Go runtime construct that can help user control how aggressive the Go garbage collector is. So let's see how it works using an example. So let's assume that the Go binary is running with 100 megabyte of allocated objects right now. So it's using 100 megabytes. And the GoGC value is set at 100. So what this means is Go's runtime will wait for 100% of new allocation, which means it will wait for the memory utilization to reach to 200 megabytes before it triggers the garbage collection. You can see on the right, if you set GoGC to 50, the Go garbage collection will be triggered when the utilization reaches 150. So comparing both of them, we can clearly see that setting GoGC to 50 made Go garbage collection more aggressive. We actually noticed this after the fine-tuning, that the rate of GoGC cycles doubled when GoGC was set to 50. Not just that, the amount of memory or bytes released also increased, and the live heap utilization of API server went down. So we then experimented with all the components in the control plane, and as a result, you can see in the graph, each of the component has a sharp decrease in the memory utilization, and over time, it stays that way. So even during peak utilization, we saw that the memory utilization was made more efficient by this simple fine-tuning technique. GoGC is a very flexible parameter. Underneath the hoods, it's a trade-off between CPU and memory. In our case, we traded off, because we were memory constrained, we traded off some CPU with efficient memory utilization. Conversely, depending on the environment, one could easily trade off memory for CPU. In fact, I have a reference from a blog from Uber. They have done exactly opposite of what we have done, where they tuned the GoGC value so that they would have lower CPU utilization, but higher memory, which is OK for their environment. So GoGC is a flexible, tunable, highly recommended. If there is a trade-off to be made between CPU memory, it is one of the things that can help with any Go program. And since Kubernetes and the control plane is Go, we use it effectively in the control plane. Moving on, the second problem that we started observing in our fleet is that, again, we are looking at the API server memory utilization graph. And you can see that the blue instance is at a much higher API server memory utilization than the green one. In fact, the skew is big enough that it started creating problems for us. What kind of problem, right? So as Ryan mentioned, if, let's say, a list request storm comes in when this queue exists in the control plane, the chances of the blue API server getting killed becomes much higher because it is consistently above average memory utilization compared to the other two. So in an unfortunate event, let's say a list storm comes in and the blue API server all of its connections are now load balanced between yellow and green. And since yellow is not much far off in terms of memory utilization, the chances of it are much higher as all the workload, all the requests from blue get transferred to yellow and green. So again, this few minutes, we would observe that the yellow API server would and then eventually, because both of them are not serving any requests now, the blue and yellow, the green API server would then not be able to handle the entire cluster's workload, and it would kill as well. So we started seeing these kinds of cascading failures in our stack. It was so bad that we actually had to set up alerts that anytime there is a memory skew, you have to go in there and take certain actions to make sure it got healed. But this was a big problem for us, and we wanted to see how we can solve it. So in digging more about this problem, we learned that anytime there was a skew in memory utilization, there was also a skew in HA proxy and API server connection. So HA proxy in our environment is just a front end, which acts as a load balancer for all the incoming traffic to API server. And it started to see a lot of skews. So you can see in the graph that the connections on 2 API servers are in the order of thousands, and the third one is just at 37. Right? So there is a big skew in the connection. And what that meant is that the rate at which each API server serves request is drastically different. You can see in the graph the green API server is serving much more number and at a higher rate of requests than the blue one. This means that because the load is different on each API server, the memory utilization will turn out to be different. Right? So all of these were symptoms of the same problem. So we started to think about how to solve this problem, right? And the most obvious intuitive feeling is, are we doing load balancing correctly in front of API server? We actually experimented with many different load balancing configurations, and none of them seem to have helped here. So what helped? We discovered a flag called goaway-chance parameter in API server. And we noticed that configuring that appropriately helped remove this problem of skews in API server. So how does it work? So when we think about requests, HTTP requests that are sent from a client to API server, underneath the hoods, they are working on established TCP connections, and these connections are long-lived. So think of this connection as pipes that are established, and think of the requests as buckets of water that can flow up and down these pipes. But once these connections are established, there's no real way for you to tear them down. So load balancing helps you in creating new connections in a fair way. But once the skew is introduced, it doesn't do anything to tear those connections down and bring up new connections. So this is where the goaway-chance parameter comes in, where it probabilistically takes some established connections in the pool and sends a go-away TCP message. What this means is it tears down the connection gracefully and allows the client to recreate the connection, hopefully going through the load balancer again and getting a better balanced traffic. What we observed is after configuring this in our API server environment, even if a skew exists, like in the graph below, within 15 minutes, the skew will automatically recover itself because this will give the API server enough chance to send go-aways to those existing connections and create new ones. Unfortunately, not a lot of documentation for this parameter exists. So I have a pull request which has a really nice description of the problem and how goaway-chance parameter solves it. This, in fact, could be used not just in the Kubernetes API server, but a similar implementation can be used in any server or any component that is doing server-side processing and load balancing in front of it. After configuring this particular parameter, we saw that there were no cascading failures in our stack anymore. So this particular configuration helped a lot in removing the control plane failures and serving GPU capacity consistently over time. So, running into these kinds of very rare scale issues, we constantly, thought, what is it with our environment that is creating these kinds of scaling issues, right? And over time, we have learned that we moved our compute platform from a legacy homegrown cloud to a cloud-native computing platform. And in that move, there were some mistakes that we made. One of them was we put a large amount of data in secret as configuration or certificates for our workload. And that meant that a lot of time is taken and effort is taken both at API server as well as the client side to encode, decode that YAML, just a lot of YAML in the workload. Then the second mistake was that the client which orchestrates this GPU capacity workload across the cluster, it works with both legacy as well as the cloud native environment. And because of that, it had to make periodic list calls against our workloads. And we know that list calls against API servers are, again, a scalability issue. So both of these mistakes combined caused a lot of challenges. And all of these fine-tuning techniques that were discussed in this presentation helped us live with these challenges for a sustained amount of time. So big shout out to the Kubernetes community for having such a robust ecosystem where these kinds of techniques can be found and implemented in an easy way. Talking about future, the future seems to be very bright on this front. Big shout out to SIG API machinery. There are at least 3 initiatives, and there are much more not listed here, but these are the initiatives that will really, really help scale the control plane in a non-trivial way going forward. So very excited about the new changes coming for the control plane. Talking about the future, there is a big change coming for our stack as well, which is we're going to transition from the current implementation, which is serving GPU capacity using device plugins, to DRA. This change is big enough that we wanted to do some kind of a perf and scale testing of the control plane before taking this change in production. So in the next set of slides, I'll be talking a little bit about what this change looks like and some of the perf and scale tests and their numbers that we ran. But before we get into that, quickly talking about what the current stack looks like. On the control plane, we have API server, controller manager, and the scheduler, the normal Kubernetes stuff. But we have one more component, which is called the topo-aware scheduler. This scheduler does NUMA alignment for our workloads. So the workloads that we are running are not just GPU workloads, but because they are high sensitive, high performance workload, we need to do NUMA alignment for that with the right CPU nodes. And topo-aware scheduler needs to be in the control plane to do this scheduling for NUMA alignment. On the worker nodes, we have device plugins that do the GPU allocations, but along with that, we have an NFD topology updater. This actually feeds the NUMA topology information into the control plane, which is then acted upon by a topo-aware scheduler. So this is the stack on the left that we have now. And then in the future, moving to DRA, we should be able to get rid of the topo-aware scheduler because the DRA API is rich enough to do NUMA alignment just default right out of the box by the kube scheduler. So we'll be removing the topo-aware scheduler from the control plane as well as the NFD topology updater from the worker nodes. And that will leave us with just the DRA plugins for our workloads and kube scheduler in the control plane. We actually did a deep dive about this whole orchestration in KubeCon in Salt Lake City. I encourage you guys to check that out. It has much more detail about how our stack, like what kind of problems we faced with device plugins and how DRA helps us solve those. But focusing on the control plane scalability, in order to scale test this, we wanted to find an easier and a cheaper way to scale test it. That's where we use KWOK. KWOK is Kubernetes WithOut Kubelet. And basically, it's a simulation tool which can help you create fake nodes in the cluster as well as fake pods. And then that creates additional pressure in the control plane. And we run the scale test using that. There are actually a couple of talks where we're talking about KWOK much more in detail. I encourage you guys to check that out and see if KWOK can be helpful. So with KWOK, talking a little bit about the scale test. So we had 132 cluster. We had KWOK installed, and we would scale from 0 to 4,000 workloads. And we would do that for topo-aware scheduler and DRA and compare certain metrics, right? So the first metric we compared is the scheduling latency. On the left, you can see the topo-aware scheduler, and on the right, you see the DRA scheduler. We found out that topo-aware scheduler is twice as more latency-driven as the DRA scheduler. So this metric was a win. We are OK to take this into production. The second metric was memory utilization. So in this slide, you see the topo-aware scheduler memory usage. But along with that topo-aware, we also have kube scheduler running in the control plane. So the real memory utilization in control plane is the sum of both. And we saw that at scale, it was around 1.3 gigabytes. But with DRA, it was around a gigabyte. So again, 30% memory saving with DRA. Again, this is a metric that checked out for us really nicely. The third metric we looked at was the effect of all of this orchestration on API server. And again, on the top, you can see that the topo-aware scheduler impact on API server, the API server was at around 5 gigabytes. And on the bottom, you see the impact of DRA orchestration. It was well under. Again, like a 20% better memory footprint in terms of how aggressive it is with API server. So all of these three metrics gave us a good initial reading with simulation that the new DRA stack is going to be much better for us. Not just they are going to solve like conceptual problems, but also in terms of perf and scale, it will be efficiency improvement.
Okay, I'm going to summarize a little bit here. So what are the takeaways? So we went through this journey at NVIDIA, and like I said, our goal was we wanted to have a fixed size control plane, and we wanted to see it scale independently of compute, right? We're assuming that GPUs are getting more powerful, which means more workloads. We want to see how that could work, right? Sometimes you unplug your GPUs, you put in new ones. We want to see what this would look like. So to summarize, like in our journey is that we found that we made some mistakes architecturally along the way, and we learned a bunch of things. Our journey was from a non-cloud native world to a cloud native world, so there were some things we had to learn. But it's cool. We were able to get through it. We were able to figure it out. We still run with all these secrets today. We still run with these sides of secrets, and it was great that we were able to find this great support from the community to actually pull this off. And it was cool to see like all these things, that these tunables that Alay mentioned, they all have different effects, based on your use case and your environment. So it's something to check out, as you are running into something like this, perhaps in your control plane, that there's a lot of things that you can do, to possibly help your scale, your memory usage, your CPU usage, and save some of yourself from possibly having some oons. And finally, we're really excited about what the Kubernetes community has ahead. They've done some really great work in scale and performance. A lot of the stuff like list streams and a bunch of upcoming stuff that we're going to get in the new Kubernetes releases later this year that we're going to roll out will actually make a lot of these problems go away for us. We probably wouldn't have hit them at all if we had some of the latest tech in Kubernetes. So that's also really exciting. And then finally with DRA, a really exciting feature that probably everyone is aware of. We're also really excited to use it. Really flexible way to allocate devices. Something that we're going to evaluate a lot and be rolling out into our production zones very soon. So very important for us. And Alay is going to be doing a lot of scale and performance work in that community. Okay, we'll take questions. Thank you, everybody. There's a microphone right in the middle of the room.
Quick question. Is it common to use HTTP 2 in front of API server?
Yeah. So for like the request side of it, it is HTTP 2. There are other long-standing things like log and exec, which use other protocols. But yeah, it's mostly HTTP 2.
Okay, I'm confessing I'm a big fan of classic Nginx and HTTP 1 wherever possible. Meaning short-lived connections or maybe sometimes like slightly longer-lived connections. But I think your example has just confirmed that when you have really persistent connections, it's not always to your advantage.
So I think the big one is the watch semantics. The watch, most of the watchers that get set up need a persistent connection to send events to the clients, and it would be really hard to. I would imagine it would be really hard to implement something like that with HTTP 1.
Do you also send them to go away?
I'm sorry?
Those long-lived watcher connections, are they also affected by go away?
That's a great question. So the existing connections will not be affected by goaway. It's actually mentioned in that PR description. Only the new connections that are set up will be impacted by the goaway configuration.
Thanks.